Have you ever wondered why it feels like dragging a heavy object when pushing it on rough concrete, while on a smooth, waxed floor, the same object slides effortlessly? In the energy filament theory, friction is not simply about an uneven surface. Instead, it's about the way energy filaments, tiny threads of force at the atomic level, interact with the surfaces, and how, when you push or pull an object, the microscopic interactions between the materials switch between two distinct motion modes. One mode is called the locking mode, where the textures of the surfaces are pressed tightly together, forcing the entire structure to move as a whole. The other is the sliding mode, where the filaments can shear or slip along the surface, almost like a thin fluid rearranging itself. When you try to push a box across rough concrete, the contact surface naturally falls into the locking mode, where the surfaces grip each other tightly. To make the box move, you first have to tear through this locking grip, essentially creating sliding channels. As you form each new channel, the tension in that part of the surface is released and then quickly patched up by the surrounding filaments. This transition from locked to sliding results in the squeaks you hear, the heat you feel, and the dust you see. These are all signs of this frictional process, where the otherwise smooth, ordered motion of the box gets disrupted into smaller, less efficient movements, resulting in noise and heat. The reason static friction feels large is that you have to exert extra force to create these channels, overcoming the locking mode that holds the materials together. Once the box is in motion, these channels remain in place, and the friction drops significantly because you're now only maintaining the motion by keeping the filaments in a shear flow, minimizing the loss of energy to heat and noise. Now consider a different surface, like a waxed floor or even ice. These surfaces naturally allow for a more continuous shear mode, where the filaments rearrange smoothly without needing to go through the disruptive locking, sudden release transition. In these cases, the friction is far less because the filaments continuously slip and slide along each other. When you push an object on these surfaces, there is far less energy lost to friction because the surfaces don't require such drastic disruptions to maintain the motion. The role of lubricants works in a similar way. They don't just make the surface slippery, but they introduce a layer between the surfaces that supports shear motion while effectively preventing the locking mechanism. This minimizes the frictional force by allowing the filaments to continue flowing smoothly rather than snapping back to a locked state. In the energy filament theory, what truly determines how easily something slides is not just the roughness or smoothness of the surface, but how much of the energy in the filaments at the contact surface is stuck in the locking mode. The more the filaments are locked in place, the more effort it takes to move the object. Every tiny shift in the object requires overcoming the frictional forces, which are essentially the microscopic processes of the filaments rearranging to adjust to the movement. Think about it this way: when you push an object, friction is not merely an obstacle. It's part of a complex, ongoing negotiation between the energy filaments. Every small movement of the object is an interaction with this hidden world of filaments, where energy is constantly being transferred and redistributed. The tension you feel is not just resistance. It's a deep restructuring process that takes place in the fabric of the material itself. For example, when pushing a car in motion, the tires don't just slide over the road. Instead, they are interacting with the road in a very dynamic way, creating friction that is constantly shifting between the locking and sliding modes. Each time the tires compress or stretch against the road, the energy filaments adjust the tension at the microscopic level. The more you push, the more the system of filaments tries to compensate for the change in movement, resulting in friction and heat. In a way, friction is not a singular force. It's an ongoing, micro-level process of forces being balanced, distributed, and rebalanced between the materials in question. The seemingly simple act of pushing a box or moving a car involves a multitude of energy exchanges happening within the materials and at the surfaces, as the filaments readjust, and readjust again. That's why friction doesn't simply disappear, it gets redistributed. And that's also why some objects, on some surfaces, slide with ease, and others seem to get stuck. To sum up, the the friction you experience is not just a simple force. It is the result of complex microscopic processes at play, in which the filaments of energy within the materials are continuously adjusting and redistributing. The friction is not an inherent property of the surfaces themselves but the outcome of how those energy filaments interact and reorganize in response to movement. The next time you push something across a surface, think of it as a dance between forces, with each filament shifting and adjusting to keep everything in balance, while energy and motion are constantly being negotiated. Stay tuned for the next episode, where we'll delve into the nuances of energy transfer in friction and how these microscopic interactions shape the world around us. Tap follow, share it on New Physics, Clear Universe.